Okay. Hello, everyone. As soon as the simulation opens up, we will talk about a couple of extra things for this video. Um, Simulation is opening. I just reset the console so it showed the POD key, so I don't have to reset it this time. Um, what we're going to talk about is an extension on the simulation from the reference simulation that we talked about from the design manager video. So, what we're going to look at is specifically some more of the meshing. Make sure the POD key didn't show up anywhere in here. Okay, we should be okay. Specifically the meshing. So far, we've used basically the same mesh settings for everything, and they've been polygonal. It's been a polygonal 2D mesh. Let's open that up really quickly. We have our mesh scene, and this is what our mesh looks like. It's composed of a whole bunch of polygons. I believe it's a mix of, depending on the shape, it's a mix of pentagons and hexagons, and some of them might even be slightly higher order cells in unique corner cases. And then we have basically rectangles for the prism layers nearby the surface. Prism layers will always be principally rectangular or clipped rectangles, depending on the corner geometry and things like that. A couple of these cells are triangles. Um, this isn't the greatest thing to have floating around in a polygonal mesh, but you can sometimes get it in tight curvature or tight corners. But this isn't the only type of mesh. So a lot of this video might be spent sitting around waiting for things to mesh so we can take a look at what we do. But let's take a look at this. So I'm going to save this as something else. Let's say mesh demo. Okay. So we have the ability to change which mesher we use. You can select different types of meshers. Let's deselect prism layer, deselect polygonal, and let's select a quad prism layer mesher. Our default controls should remain pretty much the same. Yeah, all these controls are going to be the same. Our custom controls should still be in effect. Nothing really changed there, except we changed it to a quad mesher. Let's execute this and see what this looks like. This might take a moment, so bear with me. Okay, maybe not actually taking all that long. I spoke slightly too soon, but no matter. So these are just different types of geometry you can use when meshing. Polygonal mesh, like I said, we have principally either hexagons or pentagons, and the prism layer is always going to be those rectangles. If you do quads, you get something that looks like this. Quads, in my experience, are kind of crap for two-dimensional stuff, because when you have curvature, how do you map rectangles to curved surfaces? The answer is with difficulty, and it looks something like this. Like, it tries to make them small, it does a good job most of the time, but like you wind up with all these weird curvature artifacts, and it can do weird stuff. This is probably going to be stable even. Like, the mesh is fine enough that it's probably still going to work. Let's run this for a little bit and see what it does. You can see the residuals start to rise up here. Take a look at a scalar scene, a vector scene. Also a plot. Let's take a look at some of these quantities and see if they're changing at all. Yeah, really, not really. Like, the residuals definitely are floating a bit. The residuals are higher because the mesh is, in general, of it's changed for starters, and it's of, in my opinion, a somewhat lower quality. It objectively has less cells to go around, and it's got all these weird corner cases going on here. But the flow field is principally the same. Lift and drag really didn't change. We can't really see any change in pitching moment. I don't think we'll be able to. We see a small blip in the center of pressure, and then it really goes back to basically exactly what it was. So this works, but it's not quite as high quality of a mesh. And if you're dealing with something that's not very well defined, like an airfoil at low angles of attack, in two-dimension, quads can potentially get you in trouble. It's not the worst thing in the world, but I prefer in the 2D polygons to quadrilaterals. Or, yeah, quadrilateral cells, so rectangles, essentially. Mostly rectangles with some, deformed rectangles to make curvatures work. So this is a quadrilateral 2D mesh. Let's see here. Yeah, so the quantities didn't really meaningfully change. Like I said, we saw a blip. We have 48579. We have 484. So it thinks the center of pressure changed by like 0.1%. Small difference. And then the Y position basically didn't change. It thinks there was a small change in the location of the center of pressure in the X direction. We have a change of like 1/10 of a Newton out of 40 for lift, and basically nothing for drag. So there's some very, very tiny changes. This is pretty insensitive to the change in the mesh in this case. Other cases might not be so insensitive. And actually, that's one of the tests to determine if your simulation is meshed finely enough. If you change the mesh and rerun it, or run it more, and your results don't change, that's good. That tells you you have a mesh that is robust. It tells you you have a mesh that is actually simulating the physics. And importantly, the results do not depend on your mesh very closely. You change your mesh and your results change a whole lot. How do you know that you're actually simulating reality? You don't, because it depends on the mesh so heavily. But if you change your mesh even significantly and the results don't change, that implies that the physics are actually being simulated accurately. So, like I said, this is what a 2D quad mesh looks like. Let's take a look at the last one, and then we'll move on to the fun topic, which is three-dimensional meshing, which will involve changing things potentially quite substantially. So we're going to select the triangular mesher, and all the same settings, just run the triangular mesher. See what happens. And while this is running, I'm going to try and look at something here. We'll see if it lets me. I'd like to take a look at... the wing and our block. And more importantly, I would like this to be a geometric representation. Okay, so here's our block. This is in 2D, so I can't actually pan this around. That's a little... hide that. Hide that. Where is our wing? There's our wing. Yeah. It's in the middle of our block, which is pretty good. Simulation domain. Oh, wait a second here. Hold the phone. It'd be so much easier if I could actually rotate this thing, but we'll get back to that in a minute. Mesh scene. Here is a whole bunch of triangles. In 2D, arguably, triangles work better than rectangles. Like, this has no obvious singularity points, kind of like the other mesh did. It has more cells. Notice, I think it went from about 140,000 cells to something like 300. Scroll up. 300,000 plus. How many iterations did it go through? Oh, there we go. Let's see here. Yeah, the previous mesh, 140,000 for the rectangular mesh. This one has pretty much double that, if not, it has more than double that. It's got like 2.5 times the number of cells. So it'll run slower, but it's of pretty reasonable quality, in my opinion. I mean, the mesh settings are all the same, so the cell sizes are principally identical. It's just a matter of we have more of them. More cells means it runs slower. So let's take a look at our scalar scene. Let's take a look at our residuals. And you can see that specifically a couple of these seem to be trending lower somewhat. Not tremendously. SDR is a little bit of an exception here. We'll give it some time for these things to stabilize here. Let's take a look at lift and drag. Basically, the graph's not changing. That's good. Again, that confirms that we are actually simulating physics. We do see a small blip in the X location of center of pressure, like before. Seems to be stabilizing. Somewhere about halfway in between previous two cases. But it's still a very small deviation. We're talking like fractions of a percent. Like a half of a tenth of a percent of a airfoil chord length. Oh, where'd the residual graph go? Yeah, so the residuals are stabilizing, maybe just slightly below where they were in some cases, maybe just where they were in others, compared to the rectangular case, and pretty darn close, or maybe slightly above where they were for the or significantly above in a couple of these cases for the polygonal case. So these meshes have different pros and cons. Triangles are very simple, but you need more of them. They have few sides for obvious reasons. Whereas polygons, you don't need as many of them, but they have more sides. So it has to do with the math of like how do you link these cells and matrix math that results from them. In general, for 2D, polygonal is my go-to because it generally results in the highest quality, most robust meshes. It doesn't always, but it usually does in my experience. Quads don't really work all that well in 2D. Triangles work pretty well in 2D, but you need a lot of them. You really do need a lot of them. So let's talk a little bit about 3D meshing. And to do this, we're going to need to do a couple things here. The first is we're going to need to get rid of this badge for 2D meshing operation and this automated 2D mesh. We're not dealing with 2D anymore. At least that's not the idea. So let's create a new geometry scene to hopefully be 3-dimensional. Geometry, surface. I don't need this to be the region. I need this to be my parts. And if it if you ever pull up a scene and it doesn't show you anything, go down here to the properties of the displayer. So this is the scene, geometry scene 2. Within it, it has a displayer, probably called surface something or other for geometry ones. Scroll down to the bottom. If it says latest surface or volume, try changing that to geometry, and I bet you your thing will show up. Except this still isn't letting me pivot this around. Tell you what, I'm going to delete that simulation. I'm going to delete this scene, and we're just going to try making a new one. Going from 2D to 3D can be a little bit awkward, but now I can actually rotate this thing around freely. Just by clicking and dragging. Oh, I don't have my mouse highlight on. Hold on a second. Okay. Sorry, I just needed to turn on a mouse highlight, so there's going to be a little bit of a jump in the video right there. Anyways, hopefully you should be able to see my mouse better now. Anywho, where was I? So I just deleted the geometry scenes. I have a new one here that is for all of these parts. I really just care about the wing and the block. And we want to make sure that we actually see the geometry representation of it. Okay. So, first off here, this has a pair of transforms, and we're subtracting air extents, and we're subtracting our wing from it. I rotated the wing actually gets rotated 90 degrees. Okay, that's part of why I'm confused. Let's change this up a little bit. Latest surface. Does that help? Right. It does help a bit. Yeah, now we have our wing that's actually sticking out of the block. I was really confused for a minute there because it didn't look like our wing was actually sticking out of this block. Now it is. And this block should be fine. So we're going to use this block for a 3-dimensional simulation. We still have our inlet. We still have our outlet. We have the top surface. Hard to read that. We have the bottom surface. We have our midplane of our wing. Pretty low aspect ratio wing. And we have the bottom of our wind tunnel. So if we have this, I'm going to take the simulation domain, and I really didn't need to delete the region. The only reason I did that was because it was giving me problems with freely rotating this view around. Now that I can freely rotate it, we're going to recreate this region by assigning parts to regions. One region for each part, one boundary for each part surface of our simulation domain. This is the exact same domain we already had. The difference is we actually care about all 3 dimensions. So to tell it we care about all 3 dimensions now, we're going to need to change our physics. So if we select our physics model, we can we must unselect 2-dimensional and select 3-dimensional instead. Should be the only change that's really needed here. Any reference values we have, there's no reference to gravity, so we should be okay. It's worth noting that in 2 dimensions, gravity defaults to the positive or the negative y direction, which would still be accurate for our case. But just so you know, in 3 dimensions, z is normally up-down. In this case, z is actually along the length of the wing. Just keep that in mind. But we did delete our region. So, we must recreate the boundary conditions. We have all the boundaries. Back, the bottom, top. We have our out of plane. And these are all going to be pressure outlets. Our inlet is going to still be a velocity inlet. And it is going to have the velocity of whatever our test velocity is. Remember, we use this as a parameter when we set the word that I'm looking for. When we set up the design manager. Previous video. We have our plane. This is not going to be a pressure outlet. This is going to be what is known as a symmetry plane. What that means is that the flow on both sides of this plane will look the same. Which makes sense if it's halfway down a wing, right? If this is the midpoint of a wing, the flow on the left should look the same as the flow on the right. So, if we're looking at half of a wing, half of a car, half of a plane, as long as we expect the flow to be symmetric, a symmetry plane is perfectly all right. And then we have a tiny, tiny, tiny surface for the trailing edge of our airfoil, and we have the rest of our airfoil. Actually, I'm going to make a small change here. This may be necessary. We will find out. I'm going to take this airfoil, and instead of just splitting off the trailing edge, I'm also going to split off the end caps. So we're going to call this wingtip. We're actually going to call both sides wingtip, even though only one of them is going to be in our domain. Create. Okay. And then we rerun our operations, and we should have a couple different surfaces. We have our wing tips. We have our wing surface, which isn't named as such. We have the wing trailing edge, which is this little tiny sliver over here. And we have everything else. So, this is what our three-dimensional computational domain looks like. It is probably reasonably sized, but it could be a little bit bigger for this case. This is a very low aspect ratio wing, so let's see based on that. So we have our wing trailing edge. We have the faces here, and I'm going to split off this wingtip. And actually, we're going to make this a new boundary. So if we want to make this a new boundary on the region level, we're going to tell it, set new boundary. Right now, the wingtip is currently part of this boundary. Select this wing.faces boundary under regions. You can see that it includes the wingtips and the rest of the surface of the wing. What I'd like to do is make it so those are separate. In practice, it probably doesn't matter, but we're going to do the same. I'm going to create a new boundary called wingtip. Attempt to do so. Oh, whoops, I messed up a little bit. Wing. Sorry, here we go. Set boundary, new. This is what we need to do. We don't actually have a region for our wing. We do have a region for our simulation domain. So if we select the wingtip, we go to set boundary, new, wing.wingtip. We can see two things. First, this boundary, wing.faces, no longer includes the wingtip. Instead, there's the wing.wingtip includes the wing. They're both still walls, they have the same boundary conditions, etc., but we can actually reference them separately. It's a pretty subtle difference, but depending on what you're trying to simulate, it could be important. For example, if you want to know a lot about the properties on this wingtip specifically, this might be a very important distinction. In other cases, it might be an unimportant distinction. But in any case, now we have our domain, we have our surfaces split, we assigned our boundary conditions already. Let's build a mesh, a three-dimensional mesh. So previously we selected automated 2D mesh and badge for 2D meshing. Now we're going to select automated mesh on our simulation domain. We have a couple options here. We're going to select surface remesher. I'll explain what that does in a minute. We're going to start with a trimmed cell mesher. I will also explain what that does in a minute. And a prism layer mesher. So, look at our default controls. We have several more than we did before. With 2D, we had only about like maybe 8 controls. Now we have something more like 12 to 14. We'll go through them. So, first off, I'm actually going to make the base size the same as we had before, 1 centimeter. CAD projection remains enabled. It really doesn't matter. Target surface size is 100. Fine. Minimum surface size, I'm going to say 3.125%. Now, notice this is a really weird number. I'll explain why this is in a minute, but suffice it to say, it's a binary divisor. It's a binary fraction of 1. You go from 1, you have it, you go to 0.5. Have 0.5, you get 0.25. You have 0.25, you get 0.125. You get 0.0625, and you get 0.03125. So 0.03125 or 3.125% is a binary fraction of 1. That's important. You'll see why. Surface proximity shouldn't matter because nothing's particularly close together, but out of an abundance of caution, I will tell it to put 5 cells in any gaps that it finds, or it try to. Surface growth rate, I'm going to leave as default. We turned this way the hell down before. We don't need to for this one. We'll see why. Prism layers we'll put back at 10. Prism layer stretching, 1.5 is probably okay. Prism layer thickness of about 50% ought to be okay. This I am not going to enable, but I will explain what it does a little bit later. Volume growth rate. This one's important. It defaults to fast. Fast is, well, fast. We're going to turn this down to very slow. Maximum cell size has defaulted to 10,000%. That's a pretty big number. Bigger than I'd like. So we don't want the biggest cell to be that big. We don't want the biggest cell to be 1 meter if our domain's only a couple meters. Even if it's like 10 meters to a side, we probably don't want that. What I will do is we'll go in binary multiples up. So 1, 100%, 200, 400, 800, 1600, 3200. Let's go with 3200. 0.32 meters will be our largest size cell. Custom controls, we want to do some refinements. First off, let's do a surface control for wake refinement. This works principally the exact same that we had before. So we select our airfoil. So we're going to select the wingtips, the trailing edge, all the surfaces on our airfoil. And we are going to tell it to refine the wake. Notice we also have more options to deal with here. We could tell it a couple different things. Couple different things to mess with here, but we're specifically looking at trimmer meshes, or trimmer wake refinement. Take a look at this. Isentropic size. We'll go with 200%. A binary multiple of our base size again. We have 100%, 200%. Pretty simple. Default growth rate is going to be very slow again. And that should be okay for the... Oh, wait, we need to select a couple more. Wake refinement. We want it to go, I think, 10 meters in... Yeah, 10 meters in X. Probably okay. Let's sweep this out by... angle. We'll sweep this out by 5 degrees. This might be excessive. We will see. And one last thing. Previously, our mesher did have this option, but this is actually important now. If we select automated mesh, if this says serial, we don't want that. For now, we're going to want to select parallel. Previously, we only had serial and concurrent. So serial is just using one processor thread for meshing it. Parallel is potentially using more than one. That can be important. So I'm going a little bit out of order here. I apologize, but we have our wake refinement. We've set our mesh base size, target size, minimum size, volume growth rate, max cell size, and the number and thickness of prism layers. The rest has been left as default. We also want to make a surface control to turn up the size on our surfaces. On basically our entire block, we're going to want the cells to be bigger. We're going to customize the target size, we're going to customize the minimum size, and we are going to disable the prism layers. Remember, prism layers only exist to model boundary layers. Boundary layers only exist adjacent to solid surfaces, or where there's two very discrete flow phenomena interacting. In this case, only interaction / flow phenomenon we have is on the surface of the wing. The surface of this block isn't actually a block, it's just a artificial cutoff to the air volume. So the only place we need a boundary layer, the only place we need a prism layer, on the surface of our wing. So I'm going to call this far field refine, because this is refining the field, mesh field, that is far away from the wing. And we're going to change this target size to the same as our maximum cell size. So these cells should start small and grow up to 3200% of base size, and by the time they're at these walls, they should be 3200% of base size. Minimum size, we're going to set it to 100%. If it needs a cell that's 1 centimeter out here, something's probably gone wrong. What else do we need? Let's add one more control for the back surface of this airfoil. Trailing edge. I want to make these cells really small, potentially. We're going to customize target and minimum. Target is going to be 25%. Minimum is going to be... Well, we'll show you another feature here while we're at it. 3.125, like it was before. Divide by 4. You can do math in these fields. You want to make something half as small and you're lazy, slash 4. Done. It'll do the math. You can see I tossed that in and it made that, it changes the absolute size, which you can see grayed out down below. So if I divide by 4, we have a little bit less than 1/10 of a millimeter. Excuse me, less than 1/10 of a millimeter. That's really small. Let's just divide by 2 instead. There we go. Now we have 0.15 millimeter. 15% of a millimeter. That's still pretty small. It probably won't actually get that small in very many places. It might not get that small anywhere, but it can get that small if it needs to. it's actually going to try and make these cells 2.5 millimeters. You know what? I'm actually going to have it again, so it's going to try and make those cells point or 1.25 millimeter. Measure. What did I just click? Ah, I know what I just clicked. So this is only in the Y direction. Oh, that was a very, very poor measure. Measuring in 3 dimensions gets wacky sometimes. Yeah, this is only about 1 millimeter tall. So we're actually going to knock this down by a factor of 4. We're going to knock this down by a factor of 8. So theoretically, it's going to try and get about 4 cells in the height of this trailing edge. Now you notice you can see all these triangles highlighted. This is actually the definition of the surface. What I did was I accidentally clicked show all meshes up here. And this is toggling on and off the definition of the geometry. So this geometry is defined by these triangles. That's what it knows this airfoil looks like. As far as it's concerned, that is this airfoil. Those triangles right there. So I'm gonna hit save. I'm gonna name this trailing edge refine, and we're going to do a couple things here. So this is a 3-dimensional mesh. This will actually generate a volume. So remember when we set this to parallel. That's important because while a 2D mesh, a surface mesh, will not use more than one thread, when you're meshing volumes, it can use more than one thread. What we'll do is we'll start by executing just the surface mesh. You can do this by right-clicking and saying execute surface mesher, or if you hit this button up here, generate surface mesh, it will run just the surface mesh part of any automated mesh nodes. This is actually running pretty fast. And if we come down here to our geometry scene, and that didn't, it is. Hold on a second here. New mesh scene. Oh, I know why it's, sorry. I know why it's doing that. We have our parts selected, not our region selected. Oh, I don't know if those are showing up. These are showing up in the wrong place, aren't they? I apologize because I've probably been doing that for a little while. These menus are showing up on my top monitor, or you can't see them. So have there latest surface. There we go. Okay, this is what our domain looks like. This is our surface mesh. Notice how these cells did get very small by the trailing edge. So it remeshed the surface. This is what that surface remesher we selected is doing. So we selected the surface remesher, and this is what it remeshed the surface. Turned these into this. That's kind of important because you'll notice these triangles are pretty big. These triangles are much smaller. And generally is going to give you much smoother curvature in a lot of places. So that's probably a pretty reasonable surface mesh. I don't like how it's growing quite that fast. So we will actually turn this down a little bit. We'll turn it down to slow. And we'll re-execute the surface mesh. Remember, this is not the volume. All this is triangles on surfaces, not the volume of the region. There's no cells in the middle here, away from the walls. These are only cells on the surface. That's still going to do user specified. What do we have? 5% before? We'll do the same thing. Okay, there we go. That's a little bit better. So it's taken quite a few layers for these cells to grow. So here's what we're gonna do. This is our surface mesh. It looks pretty reasonable, but you'll notice there's something missing here. We have our wing, but we don't have any wake refinement here. The wake refinement that we implemented is a trimmer wake refinement. And these are two different steps. So what we said is for the volume mesh, when it actually breaks this into three-dimensional chunks of space, that's the trimmer. It will refine that behind this airfoil. If we wanted to refine the surface remesher, which is what we just did behind this airfoil, we have to check this box. And notice it added a remesher wake refinement property here. So let's rerun this, and we should see a fairly large triangle extending quite a ways back of much smaller cells. And this is probably going to take noticeably longer because it's going to have significantly more cells. Okay. We'll see how much more I can get through. I do have to stuff done before I need to head to campus, but there we go. Our surface remesher now properly made the cells behind this thing much smaller. Much smaller. So that is pretty much exactly what we were after. This is still all a surface mesh. Can't run a simulation base. There is no cells in the middle here. So if we want cells in the middle, we need to actually run the volume mesher. Let's tell it to do that. We're just going to tell it to execute the entire mesh. Couple things here. Notice it checked when I told it to execute. It said surface remesher is up to date. It said, hey, you told me to make a mesh. I already have a surface mesh. I just finished that. It's up to date. I don't need to redo it. I'm going to use it. So it said, I don't need to redo the surface mesh, but instead immediately starts doing the volume mesh. So it starts by making a prism layer subsurface. So it builds out what the prism layer looks like. It built that in about 7 seconds. And now it's doing a trimmer mesh. This part may or may not take the longest. Really depends. But at this point, my computer is most definitely having a little bit of a hard time here. I can hear the fans whirling away. Let me pull up the resource monitor here, and it's not using all of the cores, but it's using a fair bit of them in different steps. Close this. There we go. Yeah, we're seeing spikes where it's using most of the CPU. Um, we'll let that finish. Mesh quality. Because this is three-dimensional, it will have many more cells. But it's also parallelized. So, which means that it's making many more cells, but it's actually using more than one core. In my case, it's using 14 cores. So, while it has more cells, it's also running faster. In this case, we have, let's do a little bit of vision here, a little bit overkill maybe. We have 12 million cells. This is quite probably a bit much, honestly. But let's take a look at what these look like. So if we go down here to our mesh scene we just made, instead of latest surface, we'll select latest surface / volume. This is what our mesh looks like in still technically 2 dimensions because we're looking on the surface. But notice they're all rectangles, or they're all squares actually, more than just rectangles. This is a trimmer mesh. And it's a trimmer mesh that's not particularly good at the back because those prism layers are really freaking compared to the other cell size. So that's a little bit awkward. We need to do something about this. I think having this prism layer thickness back here is probably a bad idea. We need to fix that. So, and the issue is mostly these cells aren't very rectangular. Like, you expect prism layers to be more like this, where they're wider than they all are tall for them, except for the very last layer, maybe. This one, they're much taller than they are wide. This is a problem. So, on the trailing edge, we're going to tell it, hey, let's go ahead and modify something about these prism layers. We're not going to turn them off. We're going to modify the total thickness of them. So we're going to make this total thickness 12.5%. 1/4 of the height. So instead of going out here, it'll go like, which should be more reasonable. We'll see. And we'll tell this mesh to run again. Execute. So, one thing about prism layers, I realize this is a lot of information, like drinking from a fire hose. Feel free to watch multiple times if needed. Prism layers don't affect the surface mesh. We can freely change the prism layers, and we did. We changed the prism layer setting, and it still thinks the surface mesher is up to date, because it is. The prism layer doesn't change the surface mesh. It only changes the volume mesh. So this is going to take another couple minutes here. We'll just give it a minute. Wait on that. It's very possible I just overdid pretty considerably the refinement on that trailing edge, and I might need to make cells bigger rather than smaller. That is entirely possible. I would argue entirely probable, even, given what I'm looking at. But we'll let that prism layer finish. We'll let this mesh finish, and then we'll take a look at it. Okay, that's still not great, but it's probably serviceable. This transition size, this aspect ratio is a lot more reasonable than it was. Um, it's probably good enough. We could also just make the cell size a little bit bigger back there, um, but I don't think we really need to. Everywhere else, it looks pretty good. Well, everywhere else that we can see. Let's keep in mind this mesh is three-dimensional. It exists inside of this entire cube. We're only looking at the surfaces of this cube, plus the surface of the airfoil. How do we look inside of this cube? Well, we're going to need to make some cuts. We'll need to cut through this so we can see what does the inside look like. We can do that. We can do it pretty easily, actually. So, first off, what we probably want to look at is a couple things. We probably want to look at, like, if we cut this wing over here, what does the mesh look like over here? We want to know that. We also want to know what the mesh looks like out here, so we probably want to cut the wing this way as well and take a look at what the mesh there looks like. If the mesh there looks reasonable and the mesh there looks reasonable, we're probably doing okay. We can do this a couple different ways. I'm going to try it this way for a second. If this doesn't work, we'll try a different way. This is using what is known as a derived part. This isn't anything actually physical. This is just a kind of theoretical part that you're using to do something that doesn't affect the physics or the mesh. It is derived from existing geometry. So, what we're going to do is create a planar section, a planar cut. Take a second because it's loading. But assuming you have a scene like this open, it should bring up a little GUI you can use to control where your planar section goes, where that planar cut goes. This might take a second. It seems to be responding. Why didn't it actually create anything? Okay, well, we'll try a different way. New part, derived part, section, plane is another way we can do it. Note, we have a whole bunch of derived parts that we can make. Some of these are pretty fancy. Some of them are very useful. However, we're going to stick to the basics. We're going to make a new derived part section plane. There, now we get our GUI. Oh, it was a cursor select. That's what was going on. I didn't realize what it was doing. We get this little handy GUI that tells us where this plane will be. We can drag it around. We can drag it around and place it where we want. Because this one happened to be by default with X normal, we can drag it into the center of our wing. We could be a little bit more precise about this if we wanted to. We could tell it, hey, your origin is at 0.5 meters exactly. Its normal is in the X direction. We could change that if we wanted it to. We could say your normal is a mix of X and Y and incline the plane. Don't particularly want that, but we could. So we're going to do this for our normal. We're going to set this to a existing displayer, and it'll add a plane that we'll be able to see in the current displayer. Since our current displayer is showing us a mesh, we don't need to create a new one. We can just say, hey, also show us this thing we're about to make. You could alternatively say no displayer, and you can add it manually. So I'm going to say existing for the moment, and we'll see what this does. In a second, we'll make another one, and we'll say no displayer for that one. See what that does. If you wanted to, you could also create many planes offset in a range. You can create planes that are some distance apart. You could create multiple arbitrary planes that are some offset from this position. It really doesn't matter. For the moment, though, we're just making one of them. So I'm going to hit create. Hey, look, it put a mesh thing here. We can't see it very clearly because everything's a little bit transparent, but we'll look at this in a moment. And next, we're going to want a plane that cuts through the wing this way. It's not at the edge, just kind of in the middle. So that would be with the Z normal. So if I select Z as our normal, drag this over, and we can set our Z to 0.5 meters. Set this to 0.75 meters. I'm trying to get it more or less in the middle of the wing. Yeah, there we go. I think this was a 3-meter span, so 1.5 meter half span. 1 meter chord, so 0.75 is halfway through our half span of our wing. And we're going to select no displayer. If we hit create this time, it didn't actually add another plane here. If I hide this one, we can see that there's nothing here now, right? We can see that this did show up, and it is showing us the mesh near this wingtip, which is serviceable, but might have some issues. You can think of what those are. Great. We'll talk about a little bit what I think those are in a little bit here. But it definitely has a mesh that will certainly run around this wingtip. It has a nice hard 90-degree corner. Nothing fancy going on there. That will produce a solution. But let's say we want to look at the other plane we just. So we're looking currently at this mesh scene 2. Here. So we can go to our displayer, mesh 1, and we need to add a derived part. Currently it's showing us the second one we made. We want it to also show us the third one we made. Just select that and click OK. And our mesh shows up. You can see it's refined behind the wing. We can see it gets very small towards the trailing edge. All kinds of other stuff. And we can see that this is 3-dimensional, right? These are all slices through the middle of our box. This mesh exists everywhere. So I'm going to go ahead and hit save. And this is going to be much slower. Much slower. And we need to update our reports really fast here. So I'm going to reselect our wing surface for lift. I'm actually going to copy this so I don't have to reselect them all manually. And we're going to select all of these and add all of these parts to all of them. All of them will reference the airfoil, trailing edge, the surface of the airfoil, and the wingtip. So the reports should be updated. Scenes. Our scalar scene is probably not showing us anything reasonable. Matter of fact, our scalar scene isn't showing us anything at the moment. We deleted what it was looking at. So we need to tell it to look at something else. We'll tell it to look at that derived plane we made that is parallel to the XY plane. Hold on. Is there a flag for 2D somewhere in here? Mostly it's just annoying because I can't just click and pivot, unfortunately. And I don't actually know how to fix that right off the top. Because I normally don't switch between 2-dimensional and 3-dimensional. It's either 2D or 3D. It's rarely ever both. So this is a little bit awkward. Effective angle 30 degrees. Update. Um, well, not really. Okay, whatever. This is still showing us a 2D plane, so that'll probably be good enough for them. Let's save that. Notice the file got a lot bigger. It's like 1.2 gigabytes, even though we don't have any actual solution. Let's initialize this real fast. It is dealing with a little bit over 10 million. So this is on this system probably going to be not all that fast. This is easily an order of magnitude smaller than most of the simulations I deal with professionally, so it's going to run faster than those. But this computer is also a lot weaker than the workstation I use professionally, so it's going to run slower than those. It's a little bit of a mixed bag. Yeah, you can see how it stopped because we hit our stopping criteria. Let me turn this up to 8,000. Oh, it's running out. So instead of going multiple iterations per second, it's taking a couple of seconds, like 5 to 6 to 7 seconds. Taking about 10 seconds per iteration. Hardly a thrilling affair to watch in real time. Actually, what the heck did I... Oh, we should probably... Let me clear the solution. I know what's going on. Our initial condition is not actually what our velocity is. So what we probably need to do, set this to our velocity, our test velocity. Everything is going to be initialized to whatever the test velocity is in the positive x direction. Let's try that again. Initialize, run. I was kind of wondering what was going on with that. Theoretically, it still would have gotten to the solution that it needed to. It just would have taken longer because it started further away from it. Right? It started everything about a factor of 4 times faster than it should have. So it's slowly figuring out what's going on here. Usually we have most of the flow is at our free stream velocity, although it's figuring out what this color bar looks like. We have a stagnation point up front. We have higher velocity under or above our airfoil. We have comparatively lower velocity underneath our airfoil. It should be generating some amount of lift. Let's see. What's it doing? Doesn't seem to be counting iterations all that well. Let's look at our axes here. Our bottom axis should have limits of 0 up to whatever. There we go. It's figuring it out. Yep, so we got lift, we got drag, and it's doing stuff. We don't have time to let it converge because this is going to take a while, but it is doing stuff. So last but not least, I wanted to go through one other thing and just look at, hey, for 3 dimensions, what the heck do some of these other meshes look like? So I'm going to stop this. I'm going to save it, and we're going to remesh twice more, just to show you, hey, what do these other meshes look like? So we're going to unselect prism layer, unselect trimmed, and we're going to select polyhedral, and we're going to select prism layer mesher. There's a couple of other meshers we could select. These are for more specialized things, which we're not going to use. And we should have a couple more options. Most of these options are going to remain the same, target size, etc. But we need to make sure anything that said trimmer now actually refers to the wake or word that I'm looking for. Actually refers to the polyhedral mesh instead now. It looks like it does. Maximum tet size is going to be 100. Volume growth rate. That all should be fine. So we're going to just not change anything. We're going to leave it alone. Notice it didn't actually redo the surface mesh again. The surface mesh is still fine. The only thing it's doing is running a different method for generating this core mesh, the mesh that is inside of this domain. So we'll need to give it a moment to finish that, and we'll see what a polyhedral mesh looks like. While we're waiting for this, a couple of notes. Trimmer meshes tend to work well for geometries where the flow direction is very dominant, going one way primarily, and it only deviates from that direction by relatively small amounts. It can do quite well at pretty much even much more complex flow fields, but it truly shines from an efficiency perspective where the flow is primarily going all in one direction. This does happen to be one of those cases. An airfoil at low angle of attack, there is some disturbance in the flow direction, pretty minimal, right? The flow is largely going in the X direction, even when it's near the surface of the airfoil at the top or bottom. If it's not at the very front, it's probably largely going in the X direction. So airfoils at low angles of attack, pretty damn good use case for a trim cell mesher. It is still very serviceable for most applications, but it is slightly less good, slightly less efficient in cases where the flow direction changes in weird increments. And that can be things like supersonic flow, where you have shock waves at arbitrary angles that change the flow by like 10 degrees or 20 degrees or 30 degrees. Trim cell meshes tend to not deal very well with that because all of these cells would have the flow going that way instead of largely that way. It doesn't like that because the flow is only exchanged through these faces. If the flow is going that way, you're going to want faces that are aligned, or on average, you'll want faces that are aligned with the flow direction. And these never will be if the flow is moving at 45 degrees. In a polyhedral mesh, though, the cell walls face all different directions, which makes it much better for distributing velocity if you have velocity going in odd directions. And we'll see this in just a minute. So for things where you have velocity, a lot of momentum moving in non-orthogonal directions in the bulk of your flow field, you probably want a polymesh. It's more expensive computationally. It takes more memory. It takes longer to compute for a given number of cells because each cell has more sides to it. In a trimmer mesh, each cell only has 6 sides, right? But it can indeed give you more stable, more robust results in cases where you have this flow that is moving at odd angle. So if you have like a complex pipe, for example, maybe a trimmer mesh isn't the thing. Maybe a polyhedral mesh is the thing you want. Or there are other meshes that can sort of give you the efficiency of a trimmer cell mesh, these cubic cells, but it will do it in a curved manner. It will curve cuboids in such a way that you still retain the efficiency of a trimmed mesh, but instead get the ability to conform to complex curves closer to what a polyhedral. It's really a trade-off. It really is. Some cases it doesn't matter a whole lot. Some cases it matters a whole lot. It's really something that you have to understand the use case and kind of have an idea of what the flow field is going to look like before you actually design your mesh. Alternatively, if you have the resources, you can iterate. If you can start with a trim cell mesher, run your case, and then see, oh, yeah, now there's a whole bunch of cells in here that are going in weird direction. Can we fix that? And then you could instead remesh it with a polyhedral mesh. Excuse me. Remesh it with a polyhedral mesh, and hopefully that would your issues. It can vary so drastically from scenario to scenario that I can't really make a universal statement when it's good, when it's bad. But there are definitely cases where a trimmer cell mesh will be less ideal than other mesh. Is it enough to matter for your intended use case? Impossible to say. It could be enough to matter. It might not be enough to matter. So I don't exactly know how close this is to done because I normally don't use polyhedral meshes. Not super familiar with the text that's flying by here. It's clearly done with part of it because it finished with a tetrahedral mesh of some kind. I believe what it's trying to do is merge various tetrahedral cells, so basically non pyramid shape, triangles in 3-dimensional space. Pyramid shaped, but not uniform, not actual perfect pyramids. Is trying to merge them into blocks, which are like a dodecahedron, things like that. We'll give it a couple more minutes here. I'm probably not going to get the chance to show you the tet mesh in this video, which is the tetrahedral mesh, but we will see. In any case, this isn't particularly going to be necessary. This isn't necessary if you're doing just a 2D mesh. This is purely for your knowledge of what will be coming for 3-dimensional things. And this cell count is honestly pretty big. Bigger than what you should probably need for any of the projects that we'll be doing. I just tend to go a little bit overkill because, again, professionally, I have access to pretty powerful computers where it doesn't matter a whole lot if I add an extra 10 million cells here or there. It'll still run in a reasonable-ish time frame. In your case, though, we're probably memory limited, which means we need to be much more careful about the number of cells. It means keeping it below probably 7 or 8 million is going to be necessary for most of the equipment that you probably use. More robust machines can run more, certainly, but you probably, for the applications that will develop, you should need more. I hope it's going to be done at some point. You can see just in the meshing operation, it's calling out how much memory it's using. In a lot of these steps, it's using approaching 2 gigabytes of memory. In my particular case, there's gobs of it. I think this is a 64 gig machine. This is a 64 gig. So I really don't, and you can see most of that is StarCCM actually. Most of that is these 14 different processes, excuse me, for StarCCM Plus are using a whole lot. But you don't need that much. Okay, it's almost done. So what it's doing now is, or what it was doing right there, was it took the solution data that we had, and it's interpolating these rectangular blocks onto the polyhedral cells. You notice how it just went from nice rectangles to all jagged? Look at the mesh. It's now a whole bunch of polygons, 3-dimensional ones, everywhere. And clearly, if the flow is going, largely this way instead of this way, there's enough cell faces that are facing every which direction that it'll figure out what the flow's doing. It'll figure out what the flow's doing pretty nicely, actually. And these faces might be nice, neat polygons, hexagonal in nature. But on the inside, it does weird things to actually get them to meet up. You clip through polygons at odd angles, you get shapes. But this is a polygonal mesh. It has actually considerably fewer cells. It has noticeably fewer cells. It's got less than 10 million cells, as opposed to what we had previously, which was more than that. I don't know by how much. This is the trimmer mesh that we had earlier. Okay, it knocked off like 500,000 cells or 1,000,000 cells. Not a huge, or like, 500,000. A little bit more. It knocked off like 0.7 million. But each cell has a lot more faces, so running this would take a lot longer. I actually have to go. But yeah, so this is a crash course, and I will have to go slower through a video that goes through this in more detail. This is kind of look ahead for what will be coming. 3-dimensional stuff will be needed. Usually not polygonal. You can usually use a trimmer mesh. But this is what a polygonal mesh looks like. We saw what a trimmer mesh looked like. Now, I wish I had an undo button. You'll notice the software doesn't have one. I'm going to switch this back to trimmer. The important thing about a trimmer mesh, and I'm not going to get the chance to show you here, we'll have to talk about it later, is that when it grows cells, it only does it in increments of 2. When it makes a cell bigger, it does it by a factor of 2. When it makes a cell smaller for the next layer, further away, it does it by merging cells or splitting cells. And it always does it by a factor of 2. That's why when I was making the sizes, I always did it in increments of 2. Right? If I'm making them smaller, it went from 1 to half to 0.25, 0.125, 0.0625, 0.3125, etc. Because it's splitting by factors of 2. When I was going up, it went 100%, 200%, 400%, 800, 1600, 3200, etc. Because it's getting bigger in increments of 2. That's for a trimmer mesh only. For a polyhedral mesh, it doesn't matter. It'll do whatever the heck it wants. You could plug in odd increments. You can plug in 7.3% for a polyhedral mesh, and it will listen to you and do a pretty good job of it, by and large. But in any case, we'll leave this here, and I will post this, and we will talk again for the next class.